Everyone. I'm Rick Fienberg, AAS Press Officer, and this is our second press conference of the day, our fourth of the 233rd meeting of the American Astronomical Society here in Seattle. I'm assisted today by my AAS Media Fellow, Carrie Hensley, who's monitoring our webcast. Please, if you haven't already, do like me and silence your cell phone. We've already had one go off today, not on the podium, thankfully. If you're on the AAS press list, you're about to be inundated. There are five, count them, 5 press releases flying toward you right now. And this afternoon, I'm hoping to finally get the videos from yesterday online. So if you missed yesterday's news conferences, you'll be able to watch those on our archived press conference webcast page. So if you haven't been to a AAS press conference before, I'll just give you the ground rules. It's real easy. I'm going to introduce the topic and the panelists. They're going to speak in order. We'll hold all the questions to the end so that we don't step on anybody's time allotment. All right. So I don't know how many times we've done it, but we've had a lot of press conferences from the Sloan Digital Sky Survey because it's kind of the Energizer bunny of sky surveys. It's been around a long time, and it just keeps going and going. Today we're going to hear a number of reports from some of the latest incarnations of Sloan, which is actually many different kinds of surveys in one. So we're going to start by hearing from the project's scientific spokesperson, Karen Masters, who's now at Haverford College. She's going to talk about how does SDSS keep going and going, past, present, and future plans. Then David Nidever from Montana State University is going to talk about it is never too late to be active. APOGEE chemical abundances of the Large Magellanic Cloud reveal a lazy past and an active present. Then he'll be followed by Renbin from University of Kentucky, Science in the Library, a new library of stellar spectra. And finally, Rebecca Nevin from the University of Colorado. How do you pronounce that acronym? Is it MaNGA? Okay. Mining MaNGA for mergers. Accurate identification of galaxy mergers with imaging and kinematics. All right, and with that, I'll turn it over to Karen, and we'll get started.
Hi, everyone. I'm Karen Masters at Haverford College near Philadelphia, and I'm the scientific spokesperson for the 4th phase of the SDSS. Rick mentioned to me that he had deja vu. I think I do too. I knew he was going to say we were the Energizer bunny of science, and so I made my slide accordingly. And I hope to give you a little bit of an update of the past, present, and future of SDSS and how it is we keep going as a survey. So believe it or not, we have 19 years of Sloan Digital Sky Survey data, more than 20 years since we've been on Sky. That has totaled 15 public data releases. So our funding and our sort of collaboration, our ethos is very much open science, open data, and has been from the very beginning. Our most recent data release was data release 15, which just went live last month. We have imaging, over 35% of the sky, and millions, literally millions of spectra. 4 million, I think, is out of date, and thousands of scientific papers and hundreds of thousands of citations. So Sloan is creating a bit of a buzz at this meeting for our plates, our plug plates. There's one of them just down by the podium here. These are drilled uniquely for each patch of the sky, and so we go through quite a lot of these. We plug optical fibers into them. But just want to kind of emphasize that we're not done as a survey. We keep going. And in particular, the 4th phase that I'm the spokesperson for, we have 3 main aspects. The 4th phase will run through 2020. So APOGEE is measuring spectra of stars in our own galaxy, and infrared spectra in particular. EBOS is our sort of classic Sloan survey. It's our mapping distances to galaxies, going deeper than ever before. And MaNGA is a new kind of venture for Sloan. So instead of a single fiber on each object, we bundle the fibers, and so we can make little spectral maps of galaxies in MaNGA. And this survey is going incredibly well. So I wanted to give you some superlatives. So MaNGA is the largest survey of its kind in the world now. The most recent data release was over 4,000 unique galaxies, I think over 5,000 data cubes in total. So a data cube is illustrated here. So we don't just get an image, we don't just get a spectra, we get a cube where at each slice we get an image. So we get an image at many, many different wavelengths. Or at each point, at many, many different points, we get a spectrum. And we can do an enormous amount with this. One of the exciting things about the most recent MaNGA data release was that we released basically analysis products that will allow scientists to use these data more straightforwardly, as well as a visualization tool, which we call Marvin. So Marvin can help you look at the data now. So the galaxy image there with the little pink hexagon over it is a MaNGA galaxy, and the hexagon illustrates the region where we've bundled the fibers. Because of the Doppler shift, that means we can get the kinematics of every star in that galaxy. So that's the kinematic map where blue is moving towards us and red away from us with respect to the center of the galaxy. But we don't just get it for stars because this is Spectra. We can do it separately for gas. And actually, you can do it separately for different ages of stars, which is really cool. We also get metallicity. We can measure how many heavy elements there are at each point of the galaxy. So that's a map of that for that galaxy. Other things, so this is kind of a technical thing, D4000. It's a feature in the spectra which correlates with the age of stars. So this is kind of like mapping the ages of the stars in this galaxy. And, the H-alpha flux tells you where the stars are forming. So you get a map of current star formation. We get so many of these different maps. I've just given you some of my favorite highlights, my favorite maps from MaNGA. This enormous amount of science is coming out of this survey, which is now the largest of its kind in the world. APOGEE's superlative is that it's the only survey doing what it does in both hemispheres. So it's the only survey mapping the galaxy, taking spectra of the galaxy from both hemispheres. We have the same instrument on the Sloan Foundation telescope and the DuPont telescope, which is in Las Campanas in Chile. And you'll hear a result today, which is not possible unless we had a southern instrument. I don't want to leave EBOS out. EBOS has been busily observing, and in fact will finish observing next month, which means they're going to do all the final cosmology analysis papers in the next year. So stay tuned for cosmology, really nice, exciting cosmology results a year from now. The EBOS is kind of filling in this gap where between some of the future surveys that are coming and the previous Sloan maps. So here's a cosmology result, which Sloan contributed to in the past, the contents of the universe. This is the pie chart. 70% of the energy is dark energy, 24% dark matter, 5% atoms. With thanks to our project director who gave me this slide, we can turn this into the Sloan funding pie. How does Sloan actually do what it does? We do it with extremely little government funding. So the Department of Energy just funded about 4 or 5% of the Sloan 4 program. The Sloan Foundation gives us instrumental seed funding to get us going. That totaled about 25% this time. And our member institutes give us 70%. And we don't know if that same funding model will go on to Sloan 5, but Sloan 5 has got the Sloan funding now and is actively soliciting members to join. And instead of using human fiber optic plugs, Sloan 5 is going to move to robotic plugging and therefore be able to do many, many, many more objects, and again, in both hemispheres. So we need a new logo. That's the new logo. And Sloan 5 will be coming soon, and much more exciting science from Sloan for many years to come, I think.
Okay, so today I'd like to present some exciting results from the Sloan Digital Sky Survey on our two nearest neighbor galaxies, the large and small Magellanic Clouds, which you can see here over the Las Campanas Observatory in Chile. So one of the large outstanding questions in astronomy is how galaxies form and evolve over time. Well, we're getting a better picture of how large galaxies like our Milky Way formed. There are many more small dwarf galaxies that you can see here in this picture from a computer simulation. Dwarf galaxies are by far the most common galaxies in the universe, and we'd like to understand them better. This has been challenging because dwarf galaxies are intrinsically faint and most are very far away. But luckily we have two dwarf galaxies right next door that we can study in great detail. These are the Magellanic Clouds that you can see here and can only be observed from the southern hemisphere. The Magellanic Clouds are the largest satellite dwarf galaxies of our own Milky Way and are currently tumbling into the Milky Way. They're very nearby. In fact, they're so close that they extend over a very huge part of the sky, and it's been challenging to map out their full structure. Most past studies have really focused only on the central parts. But now that's all changing. So almost 2 years ago, the Sloan Digital Sky Survey got a new eye in the southern sky. This is the southern APOGEE spectrograph, with which we can observe 300 stars at a time in the near-infrared wavelengths over a large patch of the sky. And with this new capability, we can explore the Magellanic Clouds like never before. So how does this all work? The spectrograph breaks up the light from a star and into its individual wavelengths, and we can detect the absorption lines from atoms in the atmosphere of the star. Here's an example of two stars that are very much alike, except that the one on the top has very few heavy elements, and the one on the bottom has lots of heavy elements, and therefore lots of absorption lines. So we are obtaining precise spectroscopic observations of 5,000 stars in the Magellanic Clouds, which allow us for the very first time to create chemical abundance maps of these dwarf galaxies. This is showing our map of the heavy elements of the stars in the large Magellanic Cloud over a background optical image. And the shapes here are due to the Sloan plates, which we are using to make the observations. So stars and galaxies have different chemical compositions due to the chemical evolution that is produced by this cycle I'm illustrating here. The first stars form from dense gas clouds, and at the end of their lives, these stars explode in supernovae and pollute the surrounding gas with heavy elements. The next generation of stars then forms from that gas and has a higher concentration of those heavy elements. And this cycle continues continually in a galaxy, enriching the gas and stars with heavy elements until basically you run out of gas. And the speed at which this happens is regulated by the star formation rate in a galaxy. For the elements that we are looking at, there are two main types of supernovae that create them. So they're the high mass star supernovae. They create these alpha elements, magnesium, calcium, silicon, and others, as well as iron. The other type is the low-mass star supernovae, which create mainly iron. The other difference is that the high-mass star supernovae, they go off almost immediately once you start forming stars, and the low-mass star supernovae go off. There's a delay of about a gig-year until they start exploding. So how do we actually use the data to understand the evolution of the Magellanic Clouds? So in this plot, on the x-axis, I'm showing the total amount of heavy elements in a star formed from both types of supernovae. On the y-axis, I'm showing the ratio of those alpha elements only formed from the high-mass star supernovae over all elements. Now, at the beginning, when a galaxy starts forming stars, you just have contributions from those high-mass star supernovae. And then once that 1 gig-year has passed and the low-mass star supernovae go off, you get them forming no alpha abundances, no alpha elements, and you get a downturn. So to show how this works, I'm showing a model of the Milky Way which we got from the APOGEE data. So here we are continuously forming stars, and it's going down once those low-mass supernovae turn on. And what happens is that the Milky Way has a very high star formation rate, so it was able to form lots of heavy elements before the low-mass supernova turned on. So in contrast, if we then add the Large Magellanic Cloud to this, again, a model from our observations, this is what the LMC looks like. You can see that it formed very few heavy elements before the low-mass star supernovae turned on. And this is due to a very low star formation rate. So initially, for the first 10 gigayears, it had a very low star formation rate, 50 times lower than the Milky Way. However, it's never too late to get active. So if we look actually at the full 13 gigayears here, you can see that very recently they had an increase in the number of alpha elements due to an increase in star formation rate of about a factor of 6. This starburst was triggered by a close encounter of the Magellanic Clouds with each other. So here's the actual data, the APOGEE data in which we based these model, and you can see the lazy past and then the active future, active current. So just to summarize, we've been using the Southern APOGEE spectrograph to perform the largest spectroscopic survey of the Magellanic Clouds to date and creating chemical maps. We have found that the Magellanic Clouds had a very lazy past with a star formation rate 50 times lower than the Milky Way. In the last couple of gigayears, they had a rapid increase in their star formation rate of 6 times due to their close interaction with each other. Thank you.
Okay. So here we are announcing the first release of the MaNGA Stellar Library. MaNGA Stellar Library is a library of spectra of stars. What does that mean? It means we are providing high quality spectra like you see here at the bottom of the screen for thousands of different types of stars. And this is an essential tool that is needed by a large number of astronomers, and in particular, people who study galaxy evolution. So why do stars have anything to do with galaxies? Because galaxies are made of stars. If you take a look at any random distant galaxy you see on the screen from the Sloan Digital Sky Survey Sky Server, you see a smudge of light. And any tiny region in that smudge of light is made by millions to billions of stars. As you do in MaNGA survey, for that region, you get the combined light from all the stars. But we astronomers want to figure out what mix of stars make up that light, so that we can understand the star formation history of the galaxy, so that we can weigh the mass of the galaxy. Figure out what mix of stars are making up the light from the combined spectra. It's a bit like hearing a symphony. When you go to a concert and hear a symphony, you hear the sound of all the instruments at once, all the musical instruments at once. Each instrument playing by itself, then you would have no idea what instruments are playing. So in order to know what instruments are playing, you want to play each instrument by itself, study its tone, so that when you hear are there. This is exactly what we do in studying galaxy evolution. Now imagine a galaxy made of only 2 stars, simplified model. If you have a star 1 that have a spectrum look like this, you can see a curve on there from blue to red, and this is showing you the intensity of light at different wavelengths. You can see wiggles in there, that's spectral features. And this is another star that you can see has very different shapes and different wiggles in the curve. If you combine the light from the 2 stars, you get the combined galaxy light, as you see there. In most cases, for distant galaxies, we don't see individual stars. We see the combined light. So we want to figure out what mix of stars make up that light. So in order to do that, we need to get the spectra for each type of star by itself. And this is what the library is. So we are making a large library including thousands of different types, and just showing you some examples here from very hot stars to cooler stars. And you can see they all have different shapes. You have different wiggles in the spectra. And these here are cooler stars. And here are some giant stars. From these wiggles in the spectra, you can tell the surface temperature of the star. You can tell the size of the star. You can tell the chemical composition of the star. So because stars vary in many different chemical composition, we need to sample a large number of each individual types. So this is captured in this plot, the Hertzsprung-Russell diagram of the MaNGA Stellar Library. Each point here represents 1 star in the library. I'm showing you the vertical axis is the luminosity or brightness of the star from thin to bright, and the horizontal axis shows you the temperature of the star from hot to cool from left to right. And the size of the symbol tells you the surface gravity of the star, which is an indication for the size. So we can tell giant stars from the mean sequence dwarf stars. And the size, the color of the symbol tells you the chemical composition. So the red colors tells you those stars have more heavy elements than the sun, and the blue and purple ones shows you they have less amount of heavy elements than the sun. And you can see we have many different dots with different sizes, different colors, and different positions on the diagram. So we are trying to cover the most inclusive set of different types of stars. And this library is currently the most inclusive library that we have in the literature. So how did we do that? This is enabled by the parallel observing capability in SDSS-IV. As you see, we use these aluminum plates that we drill holes on them corresponding to positions of different stars in the sky, and then we plug fibers into them. So when APOGEE is observing in the infrared using the APOGEE fibers, we can plug a separate set of fibers into the plate targeting different stars in the same field of view. And using the MaNGA instrument, we can get observations for a lot of stars, and we get it for free. So this is how we do that. The reality is more complicated than this. I'm showing you a real picture, and you can see it's like a spaghetti monster. There's hundreds of fibers in there. So that is the presentation for MaNGA Stellar Library. We are providing a new library of stellar spectra for thousands of different types. It's an essential tool for astronomers studying the stellar makeup of galaxies. We cover a much more comprehensive set of different types of stars, and it's made possible by the parallel observing opportunity. Thank you. Bye.
Okay, can you hear me? Yes. Okay, so I'm Rebecca Nevin. I'm a graduate student at the University of Colorado Boulder, and I'm really excited to talk about some work my group has been doing with creating better identification techniques for finding merging galaxies using both imaging and kinematics from the Sloan survey. So what you're looking at in this image is a simulated merging galaxy next to a mock Sloan image I've created from that same simulation. Okay, so why do we need to learn about merging galaxies? Well, it turns out that over cosmic time, galaxies evolve in the universe from this very disorganized, not really galaxy-looking thing you're seeing on the left that's very clumpy, it's very tiny, into this more beautiful, organized spiral galaxy you're seeing on the right. That's the Andromeda Galaxy. And so galaxies over time build up their mass. And galaxy mergers are one of the processes that can drive this evolution in the universe. So here's one of my favorite galaxy mergers. This is the antennae galaxies. And in the antennae galaxies, you can see a lot of light. So I like to think of merging galaxies as more of a creative process, as in they're creating new material, and less of a destructive train wrecky type of process. Right, so what you're seeing here is the blue and the red are new star formation in this galaxy as a result of the galaxy merger. So this might seem like a very obvious thing to find in the universe. This is obviously a merging galaxy, and this is because it is a major merger, which means that it's a merger between two galaxies that are roughly equal in mass. In reality, galaxy mergers come in a surprising diversity, so it's actually very difficult to find some merging galaxies in the universe. And this is why there's some disagreement in the field of astronomy about why and how galaxy mergers are actually important to galaxy evolution. Some people might argue over if galaxy mergers are actually important to driving star formation overall in the universe. And so we can see this come into play looking at these two images, one of which is a major merger, like the one I just showed you on the left, so that's more obvious to the eye that that's a merging galaxy. And the one on the right is a minor merger, so that secondary tiny little dot is the secondary merging galaxy. This is much harder to find. Additionally, galaxy mergers persist for giga years. That means billions of years. And so this makes them very, very hard to identify because you're trying to find an instant in that very long merger. They don't always look the same throughout the duration of the merger. So what my group is trying to do is use simulations of galaxy mergers, which I'm going to show you in a minute. Specifically, my collaborator Laura Blecka at the University of Florida runs these simulations, and I will be showing you one of them. There will be a time bar along the bottom that shows the time in billions of years throughout the merger. Production quality, I made this in iMovie. So what you're seeing is the tidal tails as the galaxies interact, and you have to wait a very long time for that galaxy to come back around and finally merge. And there it comes. So this whole merger took 2.5 billion years to happen. And with these simulations, we're really able to capture more moments in time during this galaxy merger. Oops, excuse me. Moving on. And build a more complete photo album of the different stages of these merger events. And so what you're looking at now is images that I have taken and I have turned them into mock Sloan images to match the specifications of the Sloan imaging survey so that I can directly apply this methodology to identify mergers in the Sloan survey. And the analogy that I've been using here to talk about what I'm doing is imagine, decades ago, people would only take one photo of themselves maybe during their entire life. How does that photo really capture how they change on a daily basis? It just doesn't. Nowadays, people are taking multiple selfies a day. You could argue this is a bad thing, but what's actually happening is that they're capturing how they change throughout their life much better. So that's what we're attempting to do with galaxy mergers. And so what I'm doing is I'm taking images throughout this photo album and I'm extracting properties of the images, for example, how asymmetric is the light in the galaxy, and I use a machine learning algorithm to then go out and apply this technique to galaxies in the Sloan survey. So for example, here are some galaxies in Sloan that my technique identifies as merging galaxies. So the one on the right is perhaps a very obvious merger. There's a lot going on there. The one on the left, most people would identify as a spiral galaxy, so this shows how the technique is a little bit different from past techniques. Okay, so this is work that was just accepted for publication. It's out online and available for reading, some light reading. But what I'm working on next is creating a technique using some of the data from the MaNGA survey. And this is exciting because MaNGA allows us to look at the velocity of the stars in the galaxy itself. So Karen talked about this a little bit. What you're looking at is the blue stars are approaching you and the red stars are receding from you. So you're seeing this rotation here. So this is my audience participation activity. Everybody has to participate in this. I want you to vote thumbs up if you think this is a galaxy merger, and thumbs down if you think it is not a galaxy merger. Vote now. Okay, lots of thumbs down. You're correct. This is an isolated galaxy. When we look at the imaging in Sloan, it looks like a disk galaxy, and what you're seeing is that disk rotation. Level 2. Is this a merging galaxy? Thumbs up if yes. Oh, people are scared to vote. Okay, lots of thumbs up. Level 3, what is this? Thumbs up if it's merging, thumbs down if it is an isolated galaxy. Okay, great job. These last two are indeed merging galaxies, and the middle one is one of my favorite mergers in MaNGA. It's obvious in the imaging and the kinematics that this is a disturbed galaxy. However, that last galaxy, if you look at just the image, it looks like an isolated disk galaxy, and my technique from imaging alone would probably not identify that as a merger. But then when you go and look at the kinematics of the stars in the galaxy, they reveal something that the imaging alone does not show, that there's a counter-rotating feature here. And so this offers clues that will really supplement the overall classification and allow us to find more merging galaxies than with just the imaging alone. Cool, thank you.
Thank you all very much. Okay, we're going to move to Q&A. If you have a question, let's see. I need a mic handler. Jordan, are you here? I'm here. Can you be my mic handler? Great. Go grab a mic from Joe in the back there. So if you have a question, raise your hand and wait for Jordan, who's the Public Information Officer for the Sloan Project at Johns Hopkins, to come by and give you the mic, and then identify yourself and your affiliation and ask your question. And if you're on the webcast, please queue up your questions for Carrie Hensley with the text chat, and we'll get to you in a few minutes. All right, questions? Oh, come on now. Oh, here we go. Thank you, Martin.
Martin Rackler, freelance and Skyscan. Probably for David, you mentioned something that made me go, huh? And that was the LMC star formation rate increase is due to a near merger or pass with SMC, and I was thinking, oh, that's because it passed through the plane of the Milky Way that triggered that. Tell me that story.
Yeah, so the Magellanic Clouds have kind of been orbiting around each other for the last 4 gigayears, and they had a very close encounter not that long ago, and that triggered these starbursts in both galaxies, and that's why they have this rapid increase in their star formation rate. Yep. And they'll be plummeting into the Milky Way now, so the next couple gigayears they'll be absorbed into the Milky Way. Yeah.
Nola?
NolaRedSpace.com. So I actually was going to ask you what the time frame was on that, and then I can't remember my other question, but so let me ask that one first.
For which part?
The recent uptick, sorry.
About 2 gigayears ago is when that happened. So the increase of the star formation rate was by a factor of 6, roughly.
And then the other question I had was, how come the Magellanic Clouds started off so much slower in their star formation than the Milky Way?
So that's mostly just because they have a very low mass. So you have more gas, you form more stars. But actually, one of the surprising things about the Magellanic Clouds is that their star formation rate is even lower than you'd expect for their mass. So even other galaxies like Fornax or Sagittarius, which are lower mass than the Magellanic Clouds, the Magellanic Clouds have a much lower star formation rate. And that's kind of a mystery. We think that might be due to the fact that the Magellanic Clouds formed far away from the Milky Way originally in a low-density environment, and then only recently fell into the Milky Way.
Okay, other questions? Do we have any online? All right, that's my opportunity. So my question is also for David Nidever. So you showed, you showed a history of star formation in the Magellanic Clouds, and I'm wondering if you can just elaborate a little bit on how you're getting the ages, how you know that you're looking at a time sequence there, because you're looking at all the stars now.
Right. So we don't actually have ages yet for the individual stars. What we do have is their chemical makeup. And so we came up with a chemical evolution model to try to fit those that chemical makeup of the different stars. And so we can basically fiddle around with different parameters in the model, for example, the star formation rate and how that changed over time. And we basically fit that to match the data. And that's what allows us to pull out the star formation rate as a function of time. And that's what I was showing with those movies.
Right.
Yeah.
Okay. I had a question for Renbin as well. This library of stellar spectra obviously will have multiple uses. I'm wondering if you can just, other than just trying to disentangle the mix of stars that are in a galaxy, can you think about some other potential uses for this library? What other kinds of scientific investigations can you make with such a high-quality set of stellar spectra?
Yeah, it can be used in many different fields, from stellar astronomy to cosmology. So in cosmology, you quite often need to fit the spectral energy distribution of distant galaxies in order to figure out how far they are. When you don't have a spectrum, sometimes you have multiple photometry bands that you can try to use the relative flux in different bands to tell how far something is. that you would need stellar population models to do that modeling. So that relies on the stellar library, the accuracy of stellar library as well. And we use it to measure the mass of stars. So to get a stellar mass of stellar mass of distant galaxies. In galactic and stellar astronomy, you use it to measure parameters of different stars. For example, if you take any random spectrum of any random stars, you want to figure out what are the temperature, surface gravity, and the chemical composition of the star. You can use the stellar library to fit those spectra and to get the parameters. Even for people who study exoplanets, they need to subtract the stellar light in order to detect the light from the exoplanets, or to use that to measure the exact parameter for the stars. So they also need to use the stellar library as well. So it's really an essential tool used by a really wide range of astronomers.
Mm-hmm. And a question for Rebecca. You showed a picture of a spiral galaxy with a couple of spots near it, and you said that it was a minor merger. But how do you, in that particular instance, how do you confirm that that's a merger rather than a large galaxy with a couple of small satellites like, M31 with its 2 small satellites? Or are you saying that in any situation where you have a big galaxy with 2 little galaxies around it, if you wait long enough, they'll merge?
Oh, that's a good question. So what I showed with those orange-looking images, so that I know for sure because those are the simulated galaxies, right? So that's the trick, is that you use the simulation so that you know going in if something is emerging or not actively. I would say to that question, though, something that's been really interesting about applying this technique to real Sloan galaxies is that I have a tool that goes out and identifies minor mergers like the one I showed. And I have had to be the follow-up checker of, are those really minor mergers? But I haven't really developed a technique that I'm fully happy with yet. So this will be a next paper of how to confirm if it's actually finding a minor merger, or sometimes you can find something that's actually just a clump of star formation in the galaxy that might look like a secondary tiny galaxy.
So will you take spectra, basically?
Right. There's going to be multiple follow-up methods I need to develop to actually check the method for real in the Sloan galaxies. Yeah.
Okay.
It's going to be hard.
All right. We have a question over here. Please remember to identify yourself.
I am Jonathan Davis from Utah Valley University for a question for Rebecca. So you might have, might just be a follow-up on what you were just saying, but when you showed that iMovie with the 2 galaxies merging, it was a great movie, by the way. It was, at the very end, you had 2 spiral galaxies that ended up as an elliptical. Does your software have any plans in the future that you might be able to identify, how these galaxies are going to end up after they have merged? Or they'll be able to identify an elliptical that has merged or something?
Oh, I think that's a really good question. So your question is, are you able to distinguish between when it is in the merger or if it just merged? Sorry, I'm just trying to clarify.
So my question is, how do you distinguish how the galaxy is going to end up after the merger?
Right.
And does your software able to distinguish between a galaxy that has gone through a merger and whether it's going to become a spiral to an elliptical after it's finished?
Right, so you just touched on something that is actively happening in galaxy evolution, is what happens when galaxies merge. So these simulations are disk galaxy mergers, and they do form more of an elliptical looking galaxy afterwards. And I think I would just say that the technique is really strong because it identifies galaxies that are about to merge as well as galaxies that have merged. So it really incorporates multiple different things about the images. So one thing that I didn't mention that it looks at is the concentration of light. So that actually goes up for galaxies after a merger. So that's one thing that it's sensitive to, is how concentrated is the light. So it's able to find galaxies that have already merged and maybe are just done merging, and it's been only 1 billion years after the merger.
Thanks.
Okay.
Anything online? Anybody else have a question? All right, I'll have one for Karen. So you stressed that this program's been around for around 2 decades now. It's the same telescope. I remember seeing a picture when that telescope debuted as, you know, it's 2.5 meters, right? Mm-hmm. So I'm assuming that part of why this survey continues and why you keep, you invent new projects that it can do is because of instrumentation evolving, right? Which is very similar to what's happened with Hubble. It's the same telescope, but it's got all these new instruments. So can you give us just a sort of high-level idea of sort of what kind of gains you've had in terms of sensitivity over the 20 years, or in terms of your efficiency, things like that? Just how has the technology changed the way the survey is done after all this time?
Well, I think the biggest change we have coming is moving from the plug plates, where the fiber optics are plugged individually, one by hand, by people who work at Apache Point Observatory and down at Las Campanas, to Sloan 5 is developing a robotic system that's going to be able to plug many more fibers and doesn't involve pre-drilling. So these plates actually get drilled in Seattle at the University of Washington, and then get shipped to the mountain. And so Sloan 5 won't involve that. So that's going to improve efficiency. I'm going to say a lot of the efficiency in Sloan is just down to our professional observers. We have a number of observers at Apache Point Observatory who that's their full-time job, is doing the observing for us, and they're incredibly efficient. They've actually enabled, MaNGA is going to actually surpass its expectations. APOGEE is massively surpassing its expectations, largely down to the efforts of our observers. So that's not technology, and that's not quite answering your question, but it's a whole package.
Well, the D in SDSS stands for digital, and as I recall, Sloan was the first digital sky survey.
Yes.
That was what made it so special at the time.
Yeah, that's right.
But CCDs have come, a very far way in 20 years. So presumably you're using much bigger CCDs and much more sensitive CCDs. And
so we're not doing imaging anymore, right? So the Sloan camera is actually still one of the largest digital cameras in the world. It just happens to be in the basement of the Smithsonian, not on a telescope. It's surpassed by some of the newer ones, but it's still really an impressive camera. But Sloan, we have a relatively small telescope. It's actually about the same size as the Hubble Space Telescope. It's just not in space. And the niche has been taking Spectra and being incredibly efficient at taking lots and lots of spectra of lots and lots of things in one night. So.
Can I help answer the question?
Absolutely, please.
So over the past 20 years, we have expanded in wavelength coverage. The spectrograph has gone to redder. In Sloan, in Sloan 1, we go up to 90-100 angstrom. Now the bulk spectrograph goes beyond 1 micron, and we added the infrared spectrograph, the APOGEE spectrograph, so that's a new thing. And also the number of fibers has increased significantly.
Fiber optic technology has also improved a lot. So the throughput through the fibers you're probably about to say that.
Is higher. And the spectrograph are becoming more efficient in Sloan 3 than previous. And in Sloan 4, we bundle the fibers together to make MaNGA possible. So that all these improvements are making the new capabilities possible.
Yeah. And building a second APOGEE instrument was a big deal, right? So now you were in both hemispheres, which is incredibly important for the Milky Way, because the Magellanic Clouds are only in the south, but also the bulge of the Milky Way only gets high in the sky in the south. So if you're wanting to map the whole Milky Way, you really want to have both. Well, see, now I sound like I'm arguing for only the south, but you want to be in the north too for the outer disk, and also for follow-up of the Kepler fields. So Renbin kind of touched on the fact that spectra of stars that are hosting exoplanets is instrumental for understanding that exoplanet system, and Sloan has been helping with that. We don't have a news item about it today, but we're still doing it.
Okay.
I was just going to add that.
Oh, sorry, go ahead. Go ahead.
I'm right here.
I'm sorry, Jen.
Hi, so to add what Karen...
This is Jen Sobek, project manager.
Oh, okay.
I get the title right. Sorry, Jen.
Yeah. It's okay. I was just going to add, actually, that our detectors, the ones that we use for the APOGEE instrument. So this allows us to push into the near infrared, which is really important because if you're looking into the galactic center, you have to penetrate through the dust. But those detectors actually happen to be cast-offs from the James Webb Space Telescope. So we have, had an evolution with regard to technology. Plus, just even going in and venturing into the near-infrared domain, we've made some really nice advancements as far as making sure that our fibers remain, cool and efficient. And then, of course, like Renbin mentioned and like Karen mentioned, there's the IFU spectroscopy as well. So yeah, we've gone through a couple of epochs of technological advancement.
One more addition.
Okay.
Oh. It's a team effort, as we're demonstrating here.
So I just want to add...
Say who you are.
Juno Kohlmeyer. I'm the director of SDSS-V, the next generation, and I just want to emphasize the power of the public data and the power of the collaboration. So SDSS reinvents itself every 5 to 6 years and is a different survey with different technology and different science goals every time. And if we're not doing the most cutting edge, interesting thing, then we're not going. And that's how we stay fresh and keep that bunny thing going.
Great, thanks. Okay.
Yeah.
Last call for questions. All right, well, there's no harm in ending a little early. It gives me time to make a few announcements to the press corps. Again, tonight we have at 5:30 in this room, we'll have a press reception with the Chandra team. Director of the Chandra X-ray Center, Belinda Wilkes, will be here to talk a little bit about Chandra's 20th anniversary. And then if you haven't yet signed up for the press dinner with the Northwest Science Writers Association, this is the last time I'm going to call and do that. Similarly, if you haven't signed up for the press tour to LIGO Hanford on Friday, and you're interested in coming along with us, please sign up for that. All right. So we're now halfway for the meeting. 4 down, 4 to go. We have briefings both Wednesday and Thursday at the same 2 times, 10:15 in the morning and 2:15 in the afternoon. Briefing at 10:15 is Things That Go Bump in the Night Sky, and we'll be hearing from the new CHIME program, looking at fast radio bursts and getting some new science from NASA's NICER experiment. So thanks again for coming today. Thanks to those of you who tuned in on the webcast, and we'll see you tomorrow morning. Thanks a lot.
It's not guaranteed, but we pitch.